Hi, I'm Danny Lahner. I'm in the 8th grade and I go to the New Century School in Baltimore City. Come with me today as we discussed one of my many interests, parachute deployment. Introduction. Standard parachute deployment works well under many circumstances. However, there are a few circumstances where it could definitely be improved. These circumstances are for lower speed applications and applications where the time before it needs to be inflated is also very low. Here's a picture of me on a vehicle that I built riding down a hill and using a drag chute that I sewed. Inspiration. This is where I got some of the ideas that make my project the way it is. And this is an airbag helmet. It deploys extremely quickly. That's ideal for parachutes. This is a vine robot. It grows out of itself, so that would be ejection. Here is a life jacket that is deployed by a toggle, similar to ripcords and other parachute deployment systems, but it's cool. It's good because we want to be able to just deploy it with a switch. And just sheer strength. This is lifting an entire person off the ground. Research question and hypothesis. Research question: can compressed gas or explosives aid in the ejection and opening and inflation of a parachute? Hypothesis 1. Parachute deployment could benefit from the use of compressed gas. Hypothesis 2. The volume of the internal structure is directly correlated to the deployment time. Definitions. Here are some definitions that you'll need to know so that you'll be able to understand the rest of the project. Shroud lines. These are the strings connecting the canopy to the bridle. Container. It's the thing holding the parachute before it starts to deploy. Ejection. It's the part of deployment where the parachute leaves the container and the lines get unfolded. Full inflation. It's when the parachute is fully opened from the oncoming wind and none of the flaps are in or collapsed. Mark. It's the version or model of something. And deployment. Deployment is from when the parachute is this period of time from when the parachute is at a state of rest in the container to when it's fully inflated. Drogue/drag chute. It's a parachute that's used to stabilize or decelerate a payload, used in space reentries and car racing. Mortar deployment. Mortar deployment is when you have a parachute inside of a cannon, and when the cannon fires, it shoots at the parachute and the parachute gets deployed. Ballistic deployment. Ballistic deployment is when you have a projectile inside of a cannon and it shoots and it pulls out a parachute canopy and it gets deployed. A spherical dome/cap. A spherical dome or cap is the shape of a sphere cut off by a plane at a point. Just like here, if you can imagine, this is 50% of a sphere and it fits perfectly on this tennis ball. So if you can imagine a tennis ball as a sphere, you cut it right there and you get this spherical dome/cap. A parachute. A parachute is a parachute whose canopy is flat. It's made of a disc of fabric when it's not inflated. A dome parachute. A dome parachute is a parachute whose canopy has a 2D surface, but its nature is to lie in 3D space. Again, spherical cap. Parachute construction, small scale model. Using 6 cores, the perimeter of the canopy is a hexagon. This is interesting because this is the one and only shape that can best approximate a sphere. The midline of each of these cores lies along the surface of the sphere. However, any other point, especially the corners, are not on the sphere. You'll notice this in figure B when you can see the corners. Again, this is a unique shape. Nothing else can approximate it. Figure C. This shows the mini parachute in construction. In figure D, we can see how the parachute pattern is different from a triangle. It differs in the shape in the sense that it's curved here, and what that does is that all along the midline, it's in full contact with the sphere. Nothing else can approximate that. And any other shape, it does not, it simply does not approximate a sphere. It's impossible to take a flat surface and turn it into a sphere. Testing environment. All the tests were performed into a makeshift wind tunnel consisting of a blower fan. In this image, we can see the blower fan and its nozzle here. This is an image of a failed Mark IV trial. Over here is an image of a Mark II trial. Blower. So here's some data from the blower fan. So we can see it's quite high up here, and as we go along here, we can see how it flattens out. The parachute was deployed in between here. Here's the raw data for your reference. Canopy 1, Mark 1 canopy plus specifications. Specifications were what I entered into the online bore generator for dome parachutes. Connecting tube, the tube diameter was 2 inches and the length was 4 feet. So as you'll notice here, again, it's the hexagonal shape over here. And that's again referencing that no matter what, the cross section of this shape will always be hexagonal. The midline will be curved and along the surface of the sphere, but always will the cross section be hexagonal. I sewed basically 2 parachute canopies together to create a double layered parachute, and you'll see why on the next slide. Marks 2 and 3 canopy. See, we can see here the Mark II canopy. So both layers of fabric of the canopy were sewn again together, so that when the air went inside, it would provide an internal structure. The geometry is actually quite complicated, but it worked nicely for Mark II and Mark III. Mark III, as you'll notice, is just another stage in the evolution of Mark II. It's just further down the line, twice as many cells, same skirt along the inside and outside. Mark IV. Mark IV was tested by doing mortar deployment using an air cannon I built for this project. Here's the air cannon with a different vine robot in a 1-inch barrel. Here is a picture of the nicely colored flaps of the canopy. Here is the pattern that I used to create the canopy. Here's the canopy in the making. Here's me sewing the canopy. Mark V. Mark V is an example of the geometrical complexity with fabric and air. Currently, we have no way to model fabric and air with computers. That's what, or we have no accurate way to, we have ways of modeling them, but they're just not quite accurate. So that technology is most certainly lacking. So that's what's making it hard in the parachute industry. Here we can see some of the choked cells. This is due probably to imprecise sewing. And here's a collapse. Materials. Testing procedures. For Mark I, I flattened the canopy and then turned on the fan. For Marks 2, 3, and 5, I flattened the canopy, attached the tube to the shop vac, and turned on the shop vac and fan at the same time via power strip. Mark IV, pack the parachute into the cannon barrel, pump up the pressure chamber to 25 psi, turn on the fan, and then shoot it into the air cannon. Mark IV was actually quite hard to test because I had to shoot it out of the air cannon, and then it had to go into the wind stream, which you can't really see. It's like aiming at an imaginary target. And then, so that's why I was only able to recover 2 successful data samples for Mark IV. Variables. The independent variable is the form of deployment. The dependent variable is the amount of time it takes for the parachute to deploy. Controlled constants were things that were held constant. Here's some raw data for your reference. Here's some raw data for your reference. Here's some raw data for your reference. Here's some raw data. And again, we'll talk about how Mark IV failed. It's because the airstream was very narrow. In a real example, we can reasonably expect that would have deployed because instead of having a narrow wind stream like this, we would have, the object would be hurtling towards the earth, and there's really no aiming involved as long as it's into the air. Data. Here are all the trials represented in the column graph. Here we can see the ticks are the averages, and Mark III is again further along the evolution process than Mark II. They're pretty similar. Summary statistics. We can see the averages of all trials and the standard deviation recovered. Comparison of the times as a whisker chart. Again, it's same information, but just a different way of looking at it. But here we can see the deviation and how much it is. It's a little bit different. Inclusion. A near instant parachute deployment system could be made based on the parachutes that I studied. The majority of Mark IV tests were invalid. This goes to show that quite possibly the testing environment doesn't suit mortar deployment. Hypothesis 1 was verified by the successful tests of Mark II, 3, and 4. Hypothesis 2. The testing of Marks 2 and 3 suggests its validity, but Mark 5 questions it. The internal geometry of the fabric and air is quite hard to even model with modern computers. The technology is lacking, and the geometry of the internal structure is very complicated. Future research possibilities may include making a more precise version of Mark V, testing other internal inflatable structures, investigating cruciform parachute canopies, creating a structural inflation system using compressed air, using explosives like those used in airbags, sodium aside, employing rigorous testing of the cannon deployment system, mortar deployment, significantly improving the deployment time of drag chutes could help pilots land gliders, prevent crashes, but more importantly, it could help save lives. References. Here's all of the things that I used for this project, all the data, all the information I used. Acknowledgements. I would like to acknowledge the following people. Mr. Brocious is my science teacher, and he gave me lots of positive feedback. I had a really nice discussion with Christopher Shreves, who works at NASA early along in the project, right as I was deciding to do parachutes, kind of before I decided what I was going to exactly do for the testing, but we had a really nice conversation. And finally, my parents really helped me a lot to understand how to make the graphs in this project and how to use Google Draw. So yeah, a big thanks to them. They also helped me understand the mathematics of this pattern and how it works. I still don't completely understand it because it is so complex, but I understand it more. So thank you to them, and thank you to you for watching.